Okay, one last lecture for autonomous differential equations, 6p2. So we'll be covering something known as phase lines. So when we have the differential equation dy dt equals f of y, what we're trying to do really is find information about y, and we're trying to figure it out given this differential equation with all sorts of methods and techniques. So we're going to be extracting more information using these things called phase lines. And what we really do is we use equilibrium points and finding the surrounding values of those equilibrium points to extract the information for the stability. So I'll explain what all that means later. So first of all, what is an equilibrium point? Well, an equilibrium point is when this is equal to 0. So it makes sense because at 0, nothing changes at 0 because it's static. So for example, if you have dy dt equals y minus 3 squared equals, you would set, if you want to find the equilibrium points of this, you would set this equal to 0. So then equilibrium points would be y equals 3. Okay, so hope that makes sense. Now we can proceed. So let's say we had the differential equation y plus 1 squared, y minus 3, y minus 5, for example. So on this, we can draw a number line like this, and then we can find where equilibrium points are, or plot where the equilibrium points are. So first one's -1, obviously, because plugging in -1, that would make the whole thing 0. Then our second equilibrium point would be at 3, because plugging in 3 would make the whole thing 0. Likewise for 5. So now we analyze the surrounding points to figure out where the solutions tend towards here, where? Well, we'll figure that out. So you'll understand it. If it's a bit confusing, you'll understand when I start actually plotting things in. So first of all, in this section, where do the solutions, or where do the y values tend to as time progresses? Well, let's figure this out. So let's just say that this is 0. We can just find the point. So at y equals 0, where does it tend to? What direction does it tend to? Well, let's see here. You can plug 0 into here, so that's 0 plus 1 squared, 0 minus 3, 0 minus 5. And that's equal to, that's 15. So it's a positive number. So when y is equal to 0, it's going towards this way. Now, however, since it's like a polynomial kind of, like it only, the derivative only changes at the sign changes, obviously. And we only observe sign changes at -1, 3, and 5, meaning that this singular case must extend to the general. So if this singular case is positive, this whole section must be positive, because the only way a derivative will ever change is if there's a sign change, which is at only -1, 3, and 5. So everything in this section here must tend towards the positive direction. And then let's try anything in this section. So this is anything negative infinity to infinity. So at y equals, I don't know, let's say -2, simplicity. dy dt equals -2 plus 1 squared, -2 minus 3, -2 minus 5. And then you don't really need to have a PhD in math to figure out that this is going to be positive, but let me just write it out anyways to show you guys. 1 times -5 times -7, that's positive 35. Positive. So it's going to tend the positive y direction as well. Note that this is a y. This is a y graph. This is y of t. Okay, so if you have, from both sides, you have one going towards that equilibrium solution and the other going away, that is known as a semi-stable equilibrium point. Okay, so now let's figure out this section here. So at y equals 3, y equals 4, dy dt equals 5 squared, 4, 1, negative 1. So this becomes negative 25, or a negative number. So here it's going to tend towards 3. And then if from both sides solutions or points are tending towards that equilibrium point, then you call that a stable equilibrium point. Okay, now let's find what 5 is. Let's classify 5. So let's say we have y equals 6, for example. So we're trying to solve for this section. dy dt equals 7 squared times 3 times 1. 49 times 3, obviously positive. I'm not going to even try to figure it out. You guys understand it's positive because it's all positive numbers being multiplied with each other. So it's going to tend towards infinity, or it's going to tend towards the positive direction. Therefore, so if you have, sorry, why did I say therefore? Okay, so if you have both sides from the equilibrium point tending towards opposite directions, that is an unstable equilibrium point. So here we classified the 3 different types of equilibrium points in an autonomous differential equation. So that was pretty much the goal of the video. I'm not going to make you guys endure another practice problem. You guys can figure it out. There's probably textbooks online. Thank you for watching, and I'll see you in the next video.